Okay, this is on. Okay, welcome everyone to my public defense of my PhD. There's quite some words in my title that some of you might not all understand, but I hope at the end of the presentation you might get a hint of what what I've been doing in this PhD. So let's first start with some context. So stars, such as the Sun and other more massive stars, are born in the interstellar medium. Their properties depend on their initial mass and their initial composition. So as they evolve, these stars will nucleosynthesize extra higher mass elements, and at the end of their lives, they will expel it. Either in case of the lower mass stars, they enter the HB phase, in which they emit their winds relatively calmly, compared to the higher mass stars, which explode in a supernova. So why is this important, this composition? Well, because our star, the Sun, and obviously our Earth, also is made of the same initial composition as from the ISM. So in this sense, the ISM is the origin of everything we have on Earth. And also the evolution of our Sun also depends on the properties of this initial composition. So how does this composition look like? So I show here now a table of Mendeleev, shaded according to which of the causes created that element. So for example, in yellow, we have the Big Bang, which created all of the hydrogen and most of the helium in the universe. Then we have HB stars, which created significant amounts of the low mass elements, so lithium, carbon, nitrogen, and then a significant fraction of the S-process elements, which are slow neutron capture elements. Then you have the typical core collapse supernova, which means heavy star just becomes too massive and the core implodes, which causes a supernova, and which creates most of the intermediate mass elements, starting from oxygen to rubidium. Then you have a few other causes, such as spallation, meaning you have hit a particle just with enough impact, and then it splits into multiple smaller pieces. You have type 1a supernova, which is just a greedy neutron star, which tries to capture increasing amount of material and then also implodes due to the Chandrasekhar limits. Then you have few unstable elements and also neutron star mergers, which can also produce some S-process elements. So this thesis is about HB stars, as you have read in the title. So what are they? They are solar-like stars up to 8 solar masses, so low mass, at the end of their lives. So in their shells, which consist of, let's say, masses up to Let me rephrase it. So they have stable core and then some unstable layers on top. And these unstable layers emit material every so often in so-called stellar winds. So what I show you here is a few pictures of HGB stars, namely of the outflows of HGB stars. So the white dot in the middle is always the star, and then you have red and blue colored stuff. The blue colored stuff is blue shifted, which means it denotes material coming towards you, and the red shifted color denotes material moving away from you. So you can see, for example, if you go to the bottom right to most, that there are different possibilities for the outflows. In this case, where my mouse now hovers, we see a bipolar outflow, meaning that the outflow goes this way and the other way. But you also see sometimes spiral-like structures, such as in the last picture, which might indicate the presence of a companion, because a single star cannot generate spiral structures. So how are these winds formed? Well, we start from the star. We have some unstable layers in the outer envelope, and that causes some shocks. Note that these shocks do not have enough velocity to make it fully out of the gravity potential of the star, so they need an extra force to travel further. And that is given by radiative pressure, But radiative pressure on what? In this case, it's radiative pressure on dust. In the stellar envelope, the material is still too hot, so dust cannot condensate. If we step a bit further outwards, then the material cools down to, let's say, 1500 degrees. Hot for us, cold for a star. So dust can form. And then radiation pressure on the dust can push the material further outwards, such that we can have a stable outflow. Now, when it's even further away from the star, then UV photons from the ISM may penetrate and may cause some dissociation, meaning that molecules may be broken up due to high energy radiation. Okay, that's most of this thing. So we have pulsations, then a wind acceleration phase, and then just a steady outflow, because both radiative pressure and the gravity potential drops at least as r to the squared, in which r is the radius to the star. So I hope I do not need to convince you that light is important in astronomy, because light impacts dynamics in RGB stars, for example, radiative pressure, which I've already talked about, and also cooling. Material cools because it just emits radiation and it goes away. So a total amount of energy must be preserved, so the internal energy drops. Great. Now, it's also important in observations. So most of the observations in astronomy are based on light. There are more recently some observations of gravity waves, but we won't be considering them in this thesis. And there are various kinds of observations. They range from just imaging the broad spectrum, so just the entire intensity field at different large frequency bands, then you can get the total luminosity of the star, and comparing them to an actual model of the star, so theoretical model of the star, you can compare the intensities and then see, well, that should be approximately the distance at which we see the star. And from the differences in intensities between the different frequency bands, you can also estimate the temperature of the star. Now, we have distances and temperatures, but we cannot really point yet directly at where the star is, because it's a bit hard to see at angles of few arc seconds. For this, you can use interferometry, because you have constructive and destructive interference. So if you have two telescopes working together, then you can get a more accurate estimate of where the star is actually pointed in the plane of the sky. And then last but not least for this thesis, we can look at spectroscopy. So the intensity of the light can vary very dramatically depending on the frequency at which we look at. That is because of the presence of atoms and molecules in these outflows of the star. These atoms and molecules each absorb or emit light at very specific frequencies, which can be seen in the spectra we obtain from the star. Okay. So we will now try to simulate how light impacts the dynamics of the AGB stars. So we need radiative transfer by definition. We need to know how light transport works in our stars. Then we will apply it to our 3D AGB models. So these are hydrodynamic models of an AGB star, optionally with a star-sized object orbiting around, if we want to do binary simulations. And then what we try to simulate is these molecular lines, which I've talked about. These can be used to infer the presence of specific molecules in the outflow and various other things, which I will talk about now, because not only the abundances or the presence can be inferred from specific lines, but also temperatures, because these lines might be excited depending on the temperature. So a molecule has different lines, and the higher the temperature, the higher these high energy lines will be excited compared to the low level lines. And you can also infer velocities due to Doppler shifts, which I will talk about in quite a few slides. So how do we simulate radiative transfer? We have a very innocent looking equation. I will just translate literally what it says. So the intensity of light in a specific direction changes due to material emitting radiation. So this is the emissivity eta minus the material absorbing radiation, which is denoted by the opacity chi. So if you go through a block of material, then you expect the intensity to change due to these two properties. Now, it seems simple, but unfortunately, there are a bit of caveats in this PhD. First of all, we have a seemingly trivial problem. We just need to model it in 3D, which is just replicating this equation a few times over to probe different directions and different positions in our model. It's simple enough, just adds a bit of computation time, but conceptually it changes nothing. Then I promised I will do a line radiative transfer, so it means that I will need to probe frequencies around these specific lines. So we do not want an equidistant frequency distribution, but just frequency distributions for us to evaluate the intensity at these specific lines. So that in itself is not too hard, except that we have my favorite thing, Doppler shifts. When Doppler shifts interact with these lines, it means that these change a bit. So what a Doppler shift is you imagine material moving towards you with a specific velocity in the line of sight. If the material moves towards you, then the frequency of the light gets blue shifted. So you have higher frequency radiation coming towards you from the point of the observer. If the thing is moving away from you, then you get a redshift, meaning that the frequency of the light is reduced when you observe it. And that causes some issues. That means that you need actually, if you look at everything you need to do in the observer frame, meaning a frame in which everything stands still, then you have different frequencies at which you need to evaluate the intensity at every point in your model. It's a bit annoying, but we can deal with it with proper interpolation and such. It's not impossible. And then we have another fun thing. We want our models to be somewhat self-consistent, NLTE. This will be talked about later, so this is just a teaser for some work you do not yet know at this point. So let me first introduce you why lines are formed. So atoms and molecules have discrete energy levels due to quantum mechanics. In order to excite a specific atom or molecule from a lower energy level to a higher energy level, you need to absorb some amount of energy which is actually equal to the energy difference between those two levels. So in case of light, if we need to absorb a photon, that photon must have exactly the right energy level, and vice versa. If an atom goes from a higher energy level to a lower energy level, it must emit a photon of this exact specific energy, such that it can transit. And this energy is just given by the frequency of the resulting photon is just given by the energy difference divided by the Planck constant. So I have now shown you a picture. So I assume this picture represents two different energy levels. So a bottom energy level, which is lower than higher energy level. Then it can move from one energy level to the next energy level by either absorbing a photon, which seems simple enough, which is denoted by the Einstein BJI coefficient to calculate the rate. Or you can have stimulated emission, in which the energy level goes from higher energy level to lower energy level. This is denoted by the BIJ, which is the Einstein coefficient for stimulated emission. And you can also just have spontaneous emission. Then it automatically, or well, randomly releases a photon without the energy, or without the radiation field having any impact. So we have emissivities and opacities. I will first explain what these equations are. So the total emissivity of a given, total emissivity caused by a certain line is given by this formula. It's just the photon energy divided by the solid angle, 4 pi, times the number density, which is the density of number of atoms or molecules at this specific energy level, at the upper energy level, times the rate of spontaneous de-excitation, the aij, times some line profile function, which I'll talk about in a next slide. And for the opacity, it's similar. So we still have the photon energy divided by 4 pi, and then we multiply it by the net rate of stimulated excitation. So the excitation rate, so BGI, minus the spontaneous, the other rate, which I've talked about in last slide, sorry. So now there's a question. Yeah, we have these level populations here. What are they? Well, we can make a guess. An initial guess is local thermodynamical equilibrium. In this case, energy levels are just given by the temperature. So from thermodynamics, you can see that if that the populations of different energy levels are related to the exponential of minus the energy difference divided by Boltzmann constant times temperature. And then, yeah, you still have non-LT, which I keep for now. Now, I said to you that that the frequency given for an emitted photon is discrete, but that's not entirely true. We have a line profile function, which just describes at what frequencies a photon can be emitted or absorbed. It's still relatively close to the actual frequency determined by the energy difference of the levels, but there are a few effects that can cause a shift from Dirac delta function to something more broader. So this line profile function encompasses thermal broadening. I've not yet explained fully what a Doppler shift are, but if you have a bunch of material, then if it's at a given non-zero temperature, then material can move at different velocities. And if it moves at different velocities, what gets emitted gets Doppler shifted differently for the different atoms which emit. So we have thermal broadening. Then we have collisional broadening. So in high pressure regimes, these molecules can collide, molecules and atoms can collide, and can also cause some differences in energy levels, which is why it's called collisional broadening. And last, and absolutely least, we have the Heisenberg uncertainty principle. Well, I said that photons are randomly emitted and they cause an energy transition. So by Heisenberg energy transition, well, yeah, there's also an uncertainty, because there's an uncertainty in the time at which it's emitted, there's an uncertainty in the energy at which it's emitted. And for HB environment, or the outflows, the thermal transitions are thermal broadening is most important. Then you can consider collisional broadening. And if you really have nothing else going on, I mean it literally, you can take into account the Heisenberg uncertainty principle. But please don't. You probably have something else. So now we can go to Doppler shifts. I've already explained to you that Doppler shifts happen because there's material moving towards you or away from you with a relative velocity compared to you. So in non-relativistic regimes, it's given by the following formula. So the Doppler shift is proportional to the original frequency at which a photon is emitted or absorbed, times the velocity difference divided by the speed of light, c. It's velocity difference in the line of sight. So yeah, for the HGB environment, we have terminal velocities, which mean that these are the velocities which the outer ends of the winds reach of about 10 kilometers per second, which actually results in Doppler shifts several times wider than the width of such a typical line profile function I've shown you. Which means you need to take it into account when calculating certain quantities. Now, I will quickly go write something on the blackboard. So if you want to, for example, compute something called the optical depth, which is the opacity integrated over the distance, then you really need to take it into account. Because naively, you might say, yeah, we need to evaluate it numerically. Let's just use the trapezoidal rule. Probably works, right? Trapezoidal rule just means, yeah, just replace this thing by difference in distance and just add up these opacities at the different positions. So at x1, at x0. Well, this works, but only if you don't have significant Doppler shifts. Because what can happen is, I will now draw something. So this is a line profile function, approximately Gaussian. And if you have significant Doppler shifts, at x0 you can maybe evaluate the frequency here, frequency at x0. At x1 you can evaluate the frequency here, frequency at x1. So if you use the trapezoidal rule, what you essentially get as outcome is a shaded area here. But what you physically have is a total area in the curve, so also this part on top. So you really need to be careful when calculating this. So, as I've shown you on the blackboard, it can impact line radiative transfer, mainly because the optical depths, which I will come to later, will be impacted. So now we're going back to LTE. So this LTE poses an assumption on the level populations that they are fully determined by the temperature. As I've said before, the successive energy levels gets less and less populated depending on the energy difference. It's given by the following formula, which Ni and Nj are the level populations, Gi and Gj are the multiplicities of these energy levels, and the rest I've already explained. E is just exponents, delta E is the energy difference, and kBt, well, kb is the Boltzmann constant, T the temperature. Now, it's nice that we have a complete prescription of the energy level distribution, but problem is this prescription is only strictly valid in a very dense medium, so we can't really use it in most of our domain, unfortunately. So we have more general NLTE. It stands for non-LTE, in which the radiation field, again, depends on the level populations Ni, but these level populations are no longer solely determined by the temperature. Instead, it depends on a combination of the radiative transitions and collisional transitions. The previous thing, it only depended in practice on the collisional transitions. Now, yeah. The radiative transitions influence them because, as I've, no. Let's just go further. So the level populations depends on the radiation field, which in turn depends on the energy levels. You see where I'm going? To know something, I need to know something else, and to know something else, I need to know something. So we need an iterative way to solve the radiation field, or to simulate the radiation field. So now here are the full equations which determine the level populations. So I'll briefly go over it. So the rate of change of the level populations must be 0 in equilibrium, and it's given by the rates of spontaneous emission minus absorption, the net absorption. Same for the second line, which just the indices are switched, so there's a minus sign. And the third line denotes the collisional transitions, so level populations times the rate at which the collisional transitions pumps it up or pumps the level population down. So now that we have a broad idea of how we can simulate radiative transfer, we still need to explain what we want to simulate with radiative transfer. So what I show you here is a line profile. So what is shown here is the flux, meaning the energy which we receive, at different frequencies. What you can see is that there are different lines present for different molecules. I'll pick one out at random, so at 340 of your, well, half between 345.5 and 346.0 gigahertz, you have the CO line, which is very strong compared to the continuum which we are looking at. The continuum, oh no, never mind. I'm wrong. It's always minus the continuum, these line profiles. So, and from this you can infer the presence of these different molecules, and depending on the shape of the line profile, you can even make an educated guess about the velocity field of the object, because Doppler shifts impact where we see the intensity at which exact frequency. Then we have another thing we want to simulate, which are called channel maps. So we once again have some intensity which we view, and we view it at different velocities. Or it's called velocities because we compare to a line which we assume to be at 0 velocity. So we compare to a specific frequency, and then we go Doppler shifting it to see at different frequencies what intensity do we get. And from this we can infer that, well, this amount of material is here moving towards or away from us. So, no. So, for example, here we have the material moving the highest velocity towards us. Then we have material with medium velocity compared to the rest of the star. And then we have material with the moving away from us the farthest relative to the star velocity. Okay, now we have a general idea of how we could simulate it and what we want to simulate with radiative transfer. We will go over with what we will be simulating radiative transfer. We will be using Magritte, which is an open source 3D NLT radiative transfer library, which has its main use in post-processing hydrodynamic simulations. So how does this work? Well, for an hydrodynamic simulation, we get some temperature, densities, and velocities out from it, but we still need a bit more. We need to augment it with some estimates of the chemical composition. So for example, I would also like, for example, CO density. You can either make an educated guess or do a chemistry simulation, which is a bit too expensive for a 3D hydrodynamics model, so I would not really recommend doing a full chemistry on this. But this temperature, density, velocity, augmented with densities of the exact molecules for which we want to simulate radiative transfer, allows us to, well, simulate what we want, because that's all the input parameters we need. Then we also obviously implement some optimizations for the radiative transfer process, including energy acceleration, which is just, energy acceleration consists of, we have slow iterations. We have some iterations of computing the level populations and then the radiation field multiple times in a row. And what energy acceleration does, at a certain point it says, yeah, we probably have some data. We can extrapolate a tiny little step from it. That's what energy acceleration does. It tries to predict some fixed points of the sequence of level populations we have computed, and thereby speeding up the process. Then you also have accelerated lambda iteration. Well, that's not important enough for this presentation, unfortunately. It's a bit too technical. So how do we use Magritte? On the left-hand side, we have a slice plot of a 3D hydrodynamics models. So what this means is you have 3D hydrodynamics models, you slice it in two, and then you look at the slice. And what we have plotted here is the CO density. So you see a star, some companion object, and a wild spiral around it. That's, for example, the input. Now what we can do is either make channel maps, as put in the top right, or just the line profile. Both of these results are made from the same initial simulation. So in the channel maps, you can see that different parts of the spiral structure move at different velocities towards and away from us, which is what we expect. Okay, now I said something in the title about optimizing radiative transfer. So I feel the need to explain to you what a big O notation means. So approximately, what it says is if you have some complicated function that you can't be bothered to write down, because it consists of all the operations I actually need to do to calculate whatever I want to calculate, and G is some approximation for it, which is fine in order of magnitude, then F is similar to big O of G, means that we can have some positive constant C, such that for large values of X, meaning that we can find the minimum value of X for which is all true, that's this F of X is smaller than this constant that we have chosen times G of X. And this can be used for determining scaling relations. So it's truly useful. So what we can do is we can try to make our own scaling relation or estimate how long it takes to compute radiative transfer. So we begin big O. So the computation time for NLT radiative transfer scales with the number of points in our models, because what we want to do is to compute, or what takes the most time is to compute this quantity Jij, which is the mean line intensity. The integral over all angles, over all frequencies of the intensity, which should be expected, multiplied with the line profile function. Integrated over frequency and angle, and for good measure, divided by 4 pi, because we've integrated over the solid angle. Okay, so our big O notation starts with the number of points. To a certain power 4 to the third, because number of model points times the average length of array is the total amount of time we need on average-ish. Then, yeah, I've put here a number of angles, so number of angles. That seems obvious. Next thing. We have a number of frequencies which we use to evaluate this thing, because we are going to evaluate this averaging over the line profile function. It doesn't need to be too much, because it just needs to evaluate it around the line center and a bit in the line wings, but we need a few. So the number of frequencies do also need. We're not done yet. We also need a number of NLTE iterations, because we want to calculate line radiative transfer self-consistently. So I'll shorten it with number of NLTE iterations. Okay, that's everything we need in total. So the goal of the thesis is, oh no, the technical goal of the thesis is to optimize this. So I will now ask the audience to guess which of these things we will not be trying to improve, of all these factors, which means either the values within these factors or some exponents or something. Keep your guess until the end of the presentation. Okay, so for better computational performance, we need to either improve or decrease the values inside these factors or decrease the exponents. Sounds simple enough. So first, we have ng acceleration. Naively, it just goes once every n steps, which n is a fixed number of steps. And it improves the performance of NLT radiative transfer quite a bit, but sometimes the choice of the number of iterations is just not optimal. So what we can do is, instead of always using a fixed number of iterations, for this example we've used 5 or something, yeah, 5. We can just choose this number adaptively, meaning that if we somehow notice, that described in the thesis, that the conversions would be slower by putting another regular iteration, then we just put an ng-accelerated step there whenever necessary. So we do the extrapolation on demand. Okay. So here is how it helps. So I have 2 complicated figures. I will explain them. So on the top, we have the maximum relative change in level populations Ni, going from step 1 to step 2 to step 3, and so on, 1 step at a time. So if we use regular ng acceleration, we have the striped lines. So on top, we have a certain benchmark model called the Van Zadelhoff model, which is used to test this ng acceleration procedure. It's just a static disk with a density which drops as r squared. Nothing special, just a disk, just a uniform thing. No, in this case, we know if we put the number of steps we need to use before each ng acceleration step too high, so this is the optically thin regime on top, it waits way too long before doing the ng acceleration step, and we do not gain enough performance out of it. On the contrast, we have the bottom figure, which is the same thing as the model as described before, but optically thick, meaning, well, that light has a harder time penetrating to it, and that it's harder to converge correctly. Where was I going with this? Yeah, just focus on the top figure for now. So you have the regular ng acceleration procedure with the striped lines, and you have the adaptive ng acceleration procedure with solid lines. And you notice that no matter which value for the maximum amount of steps we choose for the adaptive procedure, that the performance remains similar and decent, which is also important, compared to the best performing model, best performing hyperparameter value for regular ng acceleration. For the bottom, we see similar things, except, of course, that if we use the number a parameter value which is too low, that we always will always impose that the ng acceleration step happens too early for this optically thick regime. So that's one improvement we can make. So for this thing, improved. So if you've guessed it, you're wrong already. So next thing, we can, instead of using the full original hydrodynamics models, we can remesh the model a bit. Because the computation time scales with n to the power 4/3 approximately. If you reduce the number of model points by, let's say, a factor 10, which is a bit much, admittedly, then you get a more than 10 times performance increase. Of course, this comes at an accuracy penalty, so you must not just remove all points and hope that you can simulate everything with only 1 data point. That doesn't work. But you need to make a solid guess of reduction of the number of points compared to the accuracy we get. So where would be reduce the number of model points in our grids? It's quite simple. Where our model data remains constant, think about densities, temperatures, and such, we actually do not need that high of a resolution in our models. So we can generate some new sample of points such that we still treat the large gradients with a decent enough resolution, but remove the points in the regions where they're just not needed. So now I will show you a few pretty pictures, and I'll take a sip of water. So what we have here again is slice plots of the density, overplotted with the connections between model points. So all these white lines, these teeny tiny white lines, means a connection from one point to a next point to a neighboring point. So on the left, you have the original non-reduced model, which contains a lot of points. And on the right, you have a reduced version, which still contains the same structures as the model of the left, but contains, obviously, way less points. Okay, so that was the number of points. We can reduce this thing. Wait, only 4. Damn it. That's half my presentation. Whatever. Okay, quick. Angular resolution, we can also improve it. So we have, for example, if we want to determine the intensity at some point far away from a star, it has 2 main contributions, namely contribution from the local medium, which is approximately the same in every direction, and a contribution from the star, which shines a very bright light, but in a very teensy angle. So what you can do is, normally you need a very high resolution in every direction. What you can do is just take a high resolution in one direction. So that improves this thing. And then, yeah, it will be skipping half of the presentation. Fine. Okay, so back. Is there anything? Yeah, I'll quickly touch upon this thing to get the final point out of the big O notation. So you can do radiative transfer in the co-moving frame. So normally, when you're computing radiative transfer, you can't really reuse the data from one point to the next because of Doppler shifts, unfortunately. Which means that the frequencies get mismatched. So what you can do is solve it in the co-moving frame, which magically matches the frequency, magically because I don't have time. And then you can solve it in less time, because you don't need to start a new ray at every individual point. And that's all I can say about co-moving frame radiative transfer. Previously, it has mostly been done for 1D radiative transfer. We have now tried it to 3D. And it was limited to either monotonic velocity fields or limited velocity gradients due to numerical instabilities. And now, here. So we have solved numerical instabilities. I will not even be able to touch upon why they were here in the first place, by using some fun trick which adaptively changes the stencil, which we use to discretize the equations. Okay, yeah, that's about it for the presentation. Sorry, no GPU computing today, no cooling. Okay, summary. So HB stars provide a significant amount of material to the ISM, and spectral lines help us with decoding information about these distant objects. In order to compare our observations and our models, we must simulate observations using radiative transfer. But, as we've mentioned before, 3D NLT line radiative transfer simulations are computationally expensive. So in this thesis, we've explored various ways to make it more efficient in order to be able to include additional physics in our simulations, or just be able to run more simulations at once if we need to do a parameter study. Okay, thank you for your attention.
CO cooling in an AGB wind environment, and you wrote that you focus on CO cooling because it's one of the most important coolants in this environment. But is it the only one, and is it the dominant one, and what else could be important in this environment?
Yeah, it's by definition absolutely not the only one. So what do we have? We have other molecules, of course. So we have HN, A2O, which are there in decentish quantities, not the same quantities as CO, still relatively decent quantities. Then you have H alpha cooling if we have enough temperature. I'm not sure whether we reach high enough temperatures in the outflow, but H alpha cooling is mostly important in the stellar atmosphere. Do we have other things? Yeah, adiabatic cooling, of course, because we have hydrodynamics, we have adiabatic cooling. Then I can't think of anything else on top of my head. But yeah.
Okay, and then going to the rate of transfer itself, which is close to my interest, I really appreciate this Magritte code, and we've also tested it against the code that we developed. Could be better also for people online. Okay. And so one of the nice things is that Magritte is also publicly available. Now, is it easy to extend it to other environments as the one that you have applied it to? Like, for example, can you think of things that need to be changed if you would want to apply it to, for example, the interstellar medium of galaxies?
The interstellar medium. Well, depends on what you actually want to do. If you want to keep it purely for line radiative transfer, we of course still need to implement dust. Unfortunately, it's still there. But I do not think there are many different things going on there. Maybe there's few things of resolution, because if you are going for galaxies or for very large scales compared to AGB scales, there might be something to test about whether you need a few bright points in your interstellar medium of stars. But for the most part, not much needs to be changed. Some parameter values, of course, because we have some minimum line opacity and such, which multiplied with a very large distance results in a minimum optical depths of significant values. Yeah.
And you wrote also in your thesis that it's on your agenda or on the agenda of the Magritte team to extend it to continuum radiation. Can you think of how, or can you explain how difficult that transition would be, or that extension?
Well, the actual implementation without testing, not too difficult, because it's just adding an extra term to the emissivity and adding an extra term to the opacity. So if we can gather some values for the emissivity and opacity, for example, some dust tables from the CNOT database, then it should be relatively straightforward. I've already made some progress, but not yet enough to commit.
Okay, that's good to hear. I look forward to that. And then I'd like to go, can you go to slide 11? Because you showed so many beautiful equations. I want to go back to one of them. Yes.
Yeah.
If you see then the second equation there, you have a term between brackets. Yeah. What happens if you have a population inversion and that term becomes negative?
Yes. Then you have masering or lasers. So what happens? So if you have a term that becomes negative, then any optical depth you compute here becomes negative, which is not too much of a problem until you realize that the formal solution of the radiative transfer equation looks something like this. Intensity is some incoming intensity times a factor e to the minus optical depth plus some factor depending on source function, but we don't even care about this factor here. Because if this optical depth is negative, it means that the intensity gets amplified. And if the intensity gets amplified dramatically, because this is in an exponent, then some things will start to go wrong with our calculations. Practically, it means that we have a very bright light shining from the environment of the star. So the optical depth can only become significantly negative if there's no significant Doppler shift within a significantly long region within the object of interest.
Okay, thank you very much.
Thank you. The questions of Jeremy have not arrived yet, so I give the word to Ceulemans.
Thank you. So, being from computer science, I will focus more on the algorithms than on the physics. But I will end with a general question regarding the connection. My first question is on the convergence of the adaptive acceleration scheme. You have a slide with the figure.
Yep.
That's a very technical question I'm going to ask. So, yeah, this figure. What I notice here is that if you look at the classical, convergence is faster if you decrease n steps. Whereas for the adaptive, not necessarily, and even for the lowest number of steps, your adaptive scheme seems in the second case to become non-monotone in its decay. So can you explain that?
Yeah. So the figure is a bit confusing, admittedly. So in the optically thin case, the less iterations you do before you use an NG acceleration step, the better it is. That's the case on top. It holds regardless of adaptive or non-adaptive NG acceleration. But in the high optical depth case, which is the second figure, you still need a significant amount of steps before it becomes interesting to do it. Because if you look at the number of steps equals 4, the blue line, then the dotted line and the solid line are plotted exactly on top of each other, which means that the adaptive procedure did not have enough steps to become adaptive.
So you mean that the classical lines that we see that are dashed, that we don't see, are below the solid lines of the same color?
Yeah, correct.
Okay. But why is it non-monotone why is the blue line non-monotone?
Non-monotone, good question. I think it's trying to do something wrong with the extrapolation because it has not yet enough information, but I'm not sure, sorry.
Okay, second question is about your, it's also a technical question about your remeshing. So you've basically have a table in which you show that with your new remeshing strategy, you can get the time of reduction. So if you, table 3.1 in your thesis on page 56, you have the reduction time and then the time of the simulation afterwards. And what you show is that with the old method, reduction and simulation take each about half of the time, but you have reduced the time of the reduction to virtually 0 with your new method, but you've slightly increased the time of the simulation as a consequence. And I'm wondering if you then need to do, how often would you need to do these simulations? Is this a favorable gain, or in a multi-query context where you need to do multiple simulations, would you still prefer the old method?
Well, yeah, there is something to say. It depends on what you exactly want to do. If you just want to rerun the same simulation with a different CO abundance, which you take constant for every model compared to the H2 abundance, then obviously you only need to do one remeshing for all these different models. So in that case, it would, in the end, be more optimal to use the original meshing method. That I agree with. But in the case that you're just running many different snapshots of the same hydrodynamics models, you need to do a different remesh every time. So it's a trade-off. If you expect to use the model many times for different radiative transfer simulations, yes, then the old method is faster.
Okay, thank you. Then in your chapter on Magritte torch, this is about the GPU, then you have memory issues because of the memory of the GPU. And I'm wondering, how did you report your speed up? Is this, because at some point you say, we first try to compute using the original data vectors. If the algorithm fails to memory errors, we try again until what do you compare then? Do you compare all those tries plus the final simulation with respect to it, or only the final?
Yeah.
Because you waste a lot of computational effort if you have to try and then try again.
Well, it's not that much computational effort, because what I do is I try the resizing things for every data vector I need at the start of my algorithm, so it crashes probably in the start. And then for every other attempt of the same, so we have total data vector, which is, and this is, let's say, a unit of memory I can actually use. So what it tries to do first is for the total data to be put on GPU. It doesn't work. Tries then total data divided by 2 on GPU. Still doesn't work. Divided by 4. It fits. So what I do is, for the speed up, is the total. So the total time taken to do everything, including the failed attempts, which fail immediately.
Okay. And do you have measurements of how often you need to reduce? Because you say probably at the start, but did you measure this?
I've added some logging functionalities, and I've taken a look at a few. So something between 4 times and 16 times reduction. But take note of it, it's on a laptop GPU, which has not much memory, and I'm also comparing versus a small model, relatively small model. So.
And then my basically big picture type question. So in the end, you're simulating a model that needs input, and you've hinted in your presentation at the input of the chemical composition, etc. You have all of these phenomena that you describe that happen during the lifetime and during the transfer. So, but we need to know this before we can model them, and we need to do the simulations to know what is happening. So it's a bit about this cycle, and then the data that you measure somehow. You have a paper in which you displayed a small part in which the data was used to calibrate the model, right? The chapter that disappeared from your thesis.
That chapter.
I'm going in that direction. So the question I want to ask is, what do we want to learn actually from the simulations, and how can we know that what we see is physics, is an artifact of the model, or is an artifact of the simulation and the numerical errors that we make? If you...
Can you rephrase that again, because I'm feared that I might be lost.
You do a simulation, and you compare with data.
Yep, compare with data.
And then it's not identical. And then you look at the pictures, and you need to know, is this real physics that I'm seeing? Is this an artifact of the model if it's not real physics, or if it's a numerical issue, computational?
So what you're hinting about is, if our models do not exactly fit what we observe, which it never does, which part is to blame? Physics, our modeling efforts, or perhaps even our observations, which might contain some errors? I'm afraid it's more a philosophical question, because we do not really know. What we can do is, for the modeling efforts, is to do different simulations with different resolutions, such that we can at least have an idea of how wrong the modeling can be. For the physics, comparing with whether we have enough physics or not, that's we don't know by definition, because we don't have implemented we don't know which physics we still need to implement. And versus observations.
But for instance, do you have data for every parameter in the model?
Data for every parameter. Well, we have data made from hydrodynamic simulations, but these are using also assumptions on what the star should look like. So, for example, if we have an hydrodynamic simulation, what we need to know as input for this HGB simulation is some initial velocity. We need to know when it's pulsating, how it's pulsating, which we do actually not know that very well.
And can you use a simulation then to improve your knowledge on the input that you're uncertain about?
Yes, if you can notice that there is something wrong, and you can try to include extra physics to fix it, and it actually fixes it, then yes.
Okay, thank you.
Thank you. The question has arrived from Professor Yates, and I'll read it aloud. What sources of opacity are missing from the current model, and how would they affect the results?
So sources of opacity. Currently, we're doing only strictly line radiative transfers, so the continuum opacities are missing. With continuum, we mostly mean dust, if I'm correct. So dust, which is roughly smooth, can have some few spikes in the opacities at certain places because of the nature of the molecules trapped in the dust. So I think it's mostly dust, which we miss. Might be other components.
And how would it affect the results?
How it will affect the results? Well, it introduces an extra opacity term. So, there are a few known effects from dust. So, well, they allows for some extra transitions. I don't know. Let me rephrase. So what you have is regular energy levels, the vibrational levels, so V is 1 for everything, V is 1 then rotational energy levels. For CO, for example, then you can have some vibrational energy levels which are way higher in energy. So this is way higher in energy. And what some of the dust opacity might allow us to do is to allow us to excite these levels because of the exact temperature of the dust.
Okay, thank you. Then I'll pass on to Professor Jonssonqvist.
Yes, thanks, Thomas, for this very nice expose of the, well, shall we call them the beautiful difficulties with 3D radiative transfer. I want to start actually just first by connecting to this. You talk about the continuum, right? But when I put up an AGB spectra in the given bands, right? I mean, there are also very many molecular lines there. I mean, frankly, there are so many, so it basically looks like a pseudo-continuum when I just look at that. So how do you treat these type of line overlaps? And if there are also other elements than CO there, is that something that you have considered or thought about?
Well, we currently focus at only a few molecules at a time for the code, which it's mainly programming constraints, unfortunately, because what we could do is just treat these other lines, as you say, just like continuum. Just put some opacity table there, so we have opacity at some certain frequency. It can, this is not really continuum with lines, perhaps. So what we could do is just put an opacity table there and just assume that these other molecules have a given temperature in order to give them a black body radiation. So that could be done, and we're planning to implement some continuum opacities anyway, so it should be possible in the same way as we treat dust.
Yes, thanks. It might also be very interesting to explore similar ideas for spectral lines in other domains, particularly from the UV domain there. Anyways, then I had a few more, so to say, broader, because you're dealing with big numerical models here, radiative transfer, and often these type of 3D radiative transfer products, they start out like very nice and, okay, we're going to do this one code package and it's going to be generally applicable, and then one ends up, applying it very in a specific domain because of these type of things. It depends on what capacities you need, depends on how much overlaps you have. do you have some, how far are we away, would you say, to have like a real 3D transfer package that could be more broadly, generally applied in astrophysics, so to speak?
Do I have an idea how this can be done? So, yeah, good question. So, in theory, what could be done is that Magritte could be used for everything, but then we need to implement everything. And that's mainly the issue with general broad radiative transfer packages for everything. Well, either it becomes a mess to write, or it probably becomes a bit too slow to use because it needs to take into account everything when you don't need everything.
No, I tend to agree with that. And then a final also on this, because in practice, of course, a lot of it, since you deal with numerical models, is about, well, computer coding. That's a lot of the daily practical work, right? And as we know, this is a field in very large change now. So if you think ahead 5-10 years from now, with what you know, what do you think our role would be then? Do we need to do any hard coding ourselves, or is it just going to be by vibe coding, and we're going to chat with our AI assistant and give them instructions, code this up for me, and give them detailed instructions what we want with our 3D radiative transfer package? Not today, but if you don't think that that's going to work in 10 years, where do you think they will fail, and where do you think we will be needed then?
Okay, so let me first talk about what I think are the constraints of current AI-generated code. So it's quite capable of doing what you ask it to do. It's not capable of knowing any nuance in what it needs to do. So if you ask it to do something, it will do it, maybe maliciously compliant, but it will try to do it at least. It will not know what it needs to do, nor why it needs to do it, so you need someone to at least oversee the coding practices. And then secondly, AI programming mainly succeeds in fields or topics where there's a lot of documentation available on the internet. For more niche topics, radiative transfer is a more niche topics, I think it might fail sometimes.
Sometimes. All right. Thanks a lot, Thomas, and congratulations.
Well, yeah. But what I've seen is it knows quite some context. Even if I use GitHub Copilot to generate some boilerplate code, which I check afterwards, it knows what a source function is, magically. So I give it some credit for that. So it's not the best thing in the world, it's not the worst thing in the world. It will be just another tool to be used to program more efficiently. That's my prediction.
Yeah. Okay. Thank you.
Thank you. But as long as AI doesn't ask questions during the defense, I think we're all safe. Are there questions from the supervisor or the co-supervisor? That's not a clear answer. Since this is a public defense, is there anybody from the audience who has a question, a remark, maybe even an objection to what has been said? Then you should ask it now. There is one. There's a question.
Maybe a more technical question, but I was wondering when I saw your meshing and you have your points and your lines connecting them to the nearest neighbors, how do you choose how many nearest neighbors a point has? Is this something variable or do you just fix it?
It's just a dollar net triangulation. So it's fixed by just making sure that the angles are not too small.
Okay. Thank you.
All right. There is another question from the audience. Excellent.
Hi, Thomas. Thank you for the presentation. Can you try and explain where the 4/3 come from in your big O notation? I didn't quite get the power.
Excellent question. So, what we try to do is, for every point in our model, so we have large model, some points in between, what we do is calculate the intensity in that point. But in order to calculate intensity at the point in the middle of the model, we need to calculate intensities at other points in the models. So on average, we need to do a calculation for one point, we need the average length of array to determine at how many points we need to calculate the intensity. And on average for a 3D thing, this results in a factor 1/3.
So it's a geometric.
Yep, it's geometric.
But then you assume that your relaxation goes linear as well, because there's never
yeah, it's not
relaxation of your
exact.
NLT system
I know.
is typically not linear, right? Or
Yes, this factor 1/3 is not exact. You have more points in the dense center and fewer on the outside when you go remeshing. Yeah, indeed.
Any further questions? Okay, if not, then the jury members will have a meeting now, and we will be back in 5 or 10 minutes. efficiently model the cellular environment. In partial fulfillment of the requirements for the PhD in science, in astronomy, and astrophysics. And Thomas Ceulemans has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of the K11, I confer upon Thomas Ceulemans the degree of Doctor in Science, Astronomy, and Astrophysics. By obtaining a doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described in the ALEA European Code of Conduct, reliability, honesty, respect, and accountability. I close the session. Congratulations. Deze twee zijn voor jou en die hebben officiële waarde, dus je mag dat absoluut niet kwijtspelen. Je komt er nog een ander, maar dit heb je nodig voor administratieve doeleinden. Ja? Oké.
Dear Thomas, dear colleagues, dear family, dear members of the jury, dear friends. Today, indeed, Thomas, it is your PhD defense. Now, your thesis, as we can see, had this ambitious title, Optimizing Line Radiative Transfer to Efficiently Model the Stellar Environment. It's a mouthful. And knowing Thomas, a carefully optimized mouthful. If you ask him what it means, and this is what we could see today, he has been explaining in great detail how photons interact with the molecules in the winds of dying stars. But if I were to translate it into everyday language, Thomas has taught the universe to compute a little faster. From the very beginning, it was clear that Thomas approached his PhD in a particular way. Quiet, precise, and with a sharp mathematical focus. Where others might say, this method works well enough, Thomas would reply, yes, but can it be made more efficient? And then he would prove that it could. But efficiency alone was not enough for him. He made the code not just faster, but also testable and reproducible, something you haven't touched upon today. In other words, he has built something that other scientists can trust, check, and build upon. And that is perhaps the highest mark of scientific integrity. Your contributions to the radiative transfer code, Margriet, are not just technical details, tucked away in the appendix of a thesis. There are solid, lasting improvements that will shape how we, your colleagues, study stars for your years to come. But the PhD is more than equations and algorithms. It is also about the community. And here too, Thomas has left his mark, in his own style. While he may not have been the loudest voice in the coffee room, he listened with great attention. While he did not join every social event, there were two constants: board game evenings and baked goods for our group meetings. About the board games, Thomas approached them with the same strategic focus as radiative transfer. For him, The rules were not obstacles, but opportunities for optimization. Did he always win? Let's just say that probability theory was often on his side. And then there was a baking. His thesis deals with radiative cooling of carbon monoxide molecules in the stellar wind, something he didn't discuss with us today. Our group meetings, on the other hand, were cooled and sweetened by his cakes. If molecules bring order to the chaos of stellar winds, then Thomas' bakings brought order to the chaos of our academic discussions. In his acknowledgements, Thomas wrote that his PhD probably took a bit longer in his perception of time than in ours. That line made me smile, because in science, time is indeed relative. A week can feel like a month when debugging a code, while 4 years of research pass by in a blink of an eye. What matters in the end is not how long it felt, but the quality of the result. And there, Thomas has delivered far beyond expectations. He has combined mathematical clarity with practical implementation. He tried to explain that to us today. He has combined scientific rigor with reproducibility. And, let us not forget, academic seriousness with a generous dose of board games and cake. Thomas, on behalf of your supervisors and the entire team that is present today, I want to thank you. Thank you for your patience, your persistence, your science, your gaming, your baking, and above all, for showing us how to do research with both precision and personality, which you don't lack. We are proud of what you have achieved, and even more proud of the person you have become during this journey. Congratulations, Thomas. You truly earned this moment, and may your next project be just as good as this one, though perhaps not quite as reproducible victorious at board games.
Thomas, of course, I also have to say a few words, but no worries, I'm going to try to keep it short, and to make sure I keep it short, I'm going to just read what is on my paper. So, 5 years ago, Thomas walked into my office to discuss a master thesis topic, and back then it was something on making radiative transfer calculations more efficient. It was a challenging topic, and I didn't know Thomas yet, so when I was explaining it to him, I was afraid it was perhaps too much or too difficult for a master thesis. Now, when I was going through the math, and I was afraid I was scaring him away with all the complexity of the project. But he immediately understood the problem, and to my surprise, at the end of that first discussion, he said something like, "Yeah, I think I can do that." Now, to be honest, at the time I was a bit skeptical, but it turned out that we were both right. Yes, it was not just a master thesis project, but an entire PhD project, and yes, you just showed us, Thomas, you could do it, and you did. Now, when you started, I had no experience supervising students. I only had a bit of experience with supercomputers. So I knew how to deal with your sheer computational power, but I also had to adjust a bit, since you're clearly not a computer, because computers always do exactly what you ask. Nonetheless, I've enjoyed many of our discussions about truly important details in algorithms and stupid but also important details in figure colors, text alignment, and all the things like that. You probably know what I mean. Now, I've always appreciated your critical thinking, your often very honest feedback, and your rich chocolate brownies. But there's one thing I truly admire about you, and that's your ability to be yourself. Even at a fancy dinner, when everyone is having wine, you order hot chocolate, because that's what you like, and you're absolutely right to do so. And I know it's a stupid example, but it clearly shows your courage and your strong character. And it's something that many people, and certainly I personally, can look up to and learn from. So thank you. Thank you for setting such an example, and of course, thank you for all your hard work on Magritte. Congratulations, Dr. Thomas Ceulemans.
First of all, thank you both for the quite great speeches, actually. Quite impressed, especially from.
Sorry, I forgot. Of course, with the speech also comes a gift. Here you go.
Yeah, sure. First, thank you all both for the great speeches. Quite honestly, I was a bit afraid that Lynn would say something a bit more inappropriate, given some history with PhD defenses, but I'm glad that it turned out great. Anyway, I would like to thank you all for the support during the years you've given me. Normally, I should have had some gifts to give you, but due to logistical errors, they are still in the reception room. But anyway, let's end this PhD defense with saying that the reception is in the first floor cafeteria of the 200D, so don't forget it, and Vrijstart at 4 o'clock.